Welcome to this explainer. If you've ever stood on a bustling platform, watching massive trains weave in and out of complex junctions, you've probably wondered how it all works without just descending into absolute chaos. Well, today, we're looking under the hood of modern transit networks. We're going way beyond just the trains and the physical tracks to examine the real strategic brain governing the whole operation: traffic management. Let's dive right in.
To really grasp why this brain is so absolutely crucial, picture this macro-level challenge. You've got a late-running high-speed service and a standard local passenger train converging on the exact same junction at the exact same time. So what actually happens when two trains need the exact same piece of track? If an operator manually holds one back, it delays the next train and the next one, creating this massive ripple effect across hundreds of miles. Solving this giant puzzle in real time is pretty much the core challenge of modern railway control.
So here's our roadmap for today. First, we'll cover the traffic management brain. Then, algorithmic conflict resolution. Third is dynamic real-time timetabling. Fourth, automatic train supervision. And we'll wrap up with proactive network optimization.
Okay, Section 1, the traffic management brain.
It helps to think of traffic management as the prefrontal cortex of the railway. It's the strategic layer of functionality sitting completely above the primary safety-critical controls, like the interlocking systems that physically stop trains from crashing into each other. Because that lower interlocking layer handles the immediate, life-or-death safety stuff, traffic management doesn't have to. Instead, its entire job is pure optimization. It moves the railway away from human operators making stressed-out reactive routing decisions and shifts it toward a system where issues are spotted and solved way in advance.
To really visualize this kind of strategic foresight, consider a standard train graph interface. You've got time running along the horizontal axis and distance on the vertical axis. A single vertical line represents the exact current time. Everything before that line is actual historical movement, already happened. But everything after it, that's a complex web of predicted movements for every single train on the network. This setup lets strategic controllers spot a scheduling conflict literally hours before it ever materializes on the physical tracks.
Moving right along to Section 2, algorithmic conflict resolution.
So when a system looks into that predicted future and sees two trains intersecting improperly, it kicks off algorithmic conflict resolution. And this happens in 3 incredibly fast steps. First, the algorithm detects that potential conflict. Second, it evaluates the routing options. And it doesn't just look at the two trains involved, it analyzes the entire board. Third, it identifies the one specific solution that minimizes overall delay across the whole system. Basically, it calculates the mathematical path of least resistance to stop that dreaded cascading delay in its tracks.
Now, you might be wondering, how does a machine actually know what the best option is? Well, these algorithms are highly customizable. Sometimes they strictly prioritize by timetable order, or they might just use a simple first-come, first-served logic. But the most advanced systems, they run a rapid-fire comparison of predicted delays for every alternative option and pick the mathematical winner. And what's really fascinating is that human operational wisdom is baked right into the code. Experienced operators actually run workshops to tailor these algorithms for the unique quirks of specific junctions.
That brings us to Section 3, dynamic real-time timetabling.
To understand how this plays out in practice, we kind of have to contrast the old way with the new way. Traditionally, railways ran on a static daily timetable, just a rigid, fixed plan downloaded once a day. If a train ran late, well, that static plan was suddenly useless, and humans had to manually route everything that fell out of sequence. Traffic management completely changes the game by introducing the dynamic, real-time timetable. This is a living, breathing schedule that is constantly evolving.
This dynamic timetable updates continuously throughout the entire day. Whenever our algorithm finds a solution to a conflict, it injects that fix directly into the living schedule. And this is huge because it empowers a vital subsystem called automatic route setting, or ARS. ARS looks at this dynamic timetable and automatically sets the routes and clears signals for the trains. Because the schedule adapts so seamlessly on the fly, ARS can handle disrupted services and out-of-sequence trains without needing an operator to constantly intervene.
But before a human controller commits to a massive routing change, they use tools like a platform docker. This is essentially a dashboard showing passenger station occupancy over time. It acts as this brilliant what-if sandbox. The operator can test out alternative rescheduling options, evaluate the real-world impact on train delays, and only then deploy their chosen option into the dynamic timetable for the automated systems to execute. It is incredibly powerful.
Let's shift gears slightly for Section 4, Automatic Train Supervision.
So, in modern high-capacity metro systems, this high-level brain is known as Automatic Train Supervision, or ATS. ATS is the subsystem responsible for overall line control. And what makes ATS so uniquely effective is its direct interface with automatic train operation. This means the strategic decisions made by the ATS algorithms don't just flip signals, they directly influence the physical movement of the automated trains themselves, entirely without a human driver involved.
ATS does this through some seriously precise interventions. It's constantly monitoring the gaps between trains. If two trains are bunching up and running a bit too close together, ATS takes immediate action. It might adjust the station dwell time, literally holding the second train at the platform for just an extra 10 seconds before letting the doors close. Or it might tell the train to coast or run at a slightly lower speed. This not only evens out the service to prevent dangerously crowded platforms, but it also saves a massive amount of electrical energy.
Because here is the real paradigm shift in a metro system. Nobody really cares if the train arrives at exactly 2:14 p.m., right? A metro values an even, predictable pulse of vehicles, say a train every 3 minutes, much more than strict adherence to some static timetable. ATS is the engine that maintains that perfect, steady heartbeat.
And finally, Section 5, Proactive Network Optimization.
When you pull all of this together, what we're really witnessing is the evolution of the railway from a reactive, human-driven system into a highly proactive, automated network. By combining conflict resolution algorithms that essentially see into the future, timetables that adapt in real time, and ATS that physically paces the vehicles, we literally turn rigid steel infrastructure into a living, proactive intelligence. The human controller's job is completely elevated from frantically pulling levers to clear traffic to strategically managing the flow of an entire ecosystem.
So, we've seen how traffic management acts as the ultimate brain, anticipating and neutralizing disruptions well before they can ripple across the network. But as these predictive algorithms get faster and our transit systems become fully autonomous, it leaves us with a pretty thrilling question to ponder. How close are we, really, to a transit network that never experiences a cascading delay at all? The invisible intelligence moving us forward is only getting smarter. Thanks for joining me on this explainer.